So it's not just the sample mean that we can actually have a distribution where it's normally distributed. So when a discrete random variable is a result of a Bernoulli process, with x is equal to the number of successes in n trials, then the result can be expressed as a sample proportion, p hat, where p hat is equal to x over n. So in this specific case, we're talking about the binomial distribution because it's a Bernoulli process or a binomial experiment, wherein the sample proportion is the number of successes that is normally that is distributed approximately normal. So whenever both n times p and n times 1 minus p are both greater than 5, the normal distribution can be used to approximate the binomial distribution. And when these conditions are satisfied and the procedure leading to the sample outcome is repeated a great many times, then the sampling distribution of that proportion will be approximately normally distributed. So the sampling distribution of the proportion, the expected value of, there should be a hot. So the sampling distribution of our proportion, the expected value of our sample proportion would be the population proportion itself, which is usually in percentage, right? Because that's how we usually have our probabilities. The standard error is this, the square root of p times 1 minus p over n, and the z-score would be p, that should just be simply p. No, not s, so it's just the s over the standard error of the proportion. It's pretty much the same when it comes to the idea. The formulas are the ones that are just different. So let's have a specific example. In number 1, it has been reported that 42.6% of U.S. workers employed as purchasing managers are females. In a simple random sample of U.S. purchasing managers, 70 out of 200 are females. Given this information, we are asked what is the population proportion, the sample proportion, and the standard error. So in number 1, we are given that it has been reported that 42.6% of the workers in US are females, workers employed as purchasing managers. And then in a simple random sample, 70 out of the 200 are females. So as you can see, the one that's 42.6%, there you go, 42.6%, that's already our population proportion. That's what has been reported. Now, it says that in a simple random sample, 70 out of 200, and that would be around 35% for 0.35, or 0.426, 0.35. This is now our sample proportion. Now, why did I write suddenly? Oops, sorry, that should be 26.426. Why did I suddenly write this in decimal? Because sometimes the computations are easier in decimal than in percentage. Right there. And then we are asked what would be the standard error of the sample proportion. Again, the formula for our standard error of the sample proportion would be P times, P times 1 minus P over N and the square root of that. So that would be the square root of, that's 0.426 times 1 minus 0.426 all over, our sample size that we mentioned is 200, so over 200. And this gives us a standard deviation rounded up to 0.0. That's for number 1. Let's now go to number 2. In number 2, the incidence of part-time working varies widely across the Organization for Cooperation and Development, or the OECD countries. The clear leader is the Netherlands, where part-time employment accounts for 33% of all jobs. Now, if a sample of 100, there you go. If a sample of 100 people of the workforce were taken in the Netherlands, what proportion between 25% and 35% in the sample would be part-time workers. So let's now go for 2A. So this 33%, that's actually the proportion for the entire Netherlands. So that's your population proportion. Now, it says that if we have a sample of 100, what would now be the proportion or the probability that the proportion is between the population proportion, the sample proportion would be between 25 to 35%. So we have to get the standard, the z-scores of 25% and 35%. And to do that, we first need to get the standard error of our proportion. And that would be coming from the square root of, that's 0.33 times 1 minus 0.33 over 100. And this gives us a standard error of, rounded up to 4 decimal places, 0.0470. With that, we can now compute the z-score of 25% and the z-score of 35%. For 25%, that would be 25% minus 33% over 0.0470. While for 35%, that's 35% minus 33% over 0.0470. Computing this, we get the z-score for 25% negative 1.70, while the z-score for 35% would be 0.43. Therefore, what we're computing is the same as finding the z-score in between negative 1.70 and 0.43. Computing for this, we get a value of 0.6218, which will mean that the probability that the sample proportion is in between 25% to 35% is actually 62.18%. So more or less, the proportion, if a sample of 100 people were taken, the proportion of that is, there's a 62.18 chance, but that's a good chance, it is between 25 to 35. Now, what if we do the exact same process, but instead of 100, we have in letter B the same population proportion, but still, but the new sample size is 200. What would now be the proportion? The sample proportion is between 25 to 35%. Pause the video and try to see if what will you be able to get. Alright, so I assume you paused the video and we computed it, so let's try now to see. First, we have our standard error, which is the square root of still 33 times 1. 33 times 1 minus 30.33 rather, but this is times 200, which gives us a standard error this time of 0.0332. So, computing now the z-scores for 25 and 35%. For 25%, we have 25 minus 32% over 0.0332. This actually gives us a value of negative 2.41. For 35%, you have 35% minus 33% over 0.0332. This actually now gives us a value of 0.60. So it will now be the same as finding the z-score in between negative 2.41 and negative 0.60. In doing so, we actually get a value of 0.7177. That means that the probability that the sample proportion would be between 25% to 35%, to 35%. If you get a sample size of 200, the proportion of that would be 71.77%. Now, as you can see, there is no mention of the population size. However, when sampling is without replacement and it's from a finite population, meaning the population size is given, the techniques that we have discussed must be slightly modified. And that slight modification is this. Whenever we're dealing with sampling distribution of the mean or the proportion, the same correction factor is applied. And it is applied when the sample size, oops, let's make it red. The sample size is at least 5 times as large as our proportion. So there you go. It should be greater than or equal to 5% of our population. With that in mind, we do the correction in our standard errors. We multiply this factor to this one and to this one if this is followed. So let's try to do it here in number 1. So we have in number 1, a firm has 290 employees that and record that they work average of 35 hours a week with a standard deviation of 8 hours a week. So let's do it again. So the firm has 290 employees, that's their population size, and the mean of that is 35 hours per week with a standard deviation of 8 hours per week. In letter A, we're asked what is the probability that an employee selected at random would be working between plus minus 2 hours per week of the population mean. Now, it only says 1 employee. And technically, a sample size of 1, an employee, that's not greater than or equal to 5% of the population size. If we want to see that, let's first get the 5% of n, which is the 5% of 290. And that will actually give us 14.5. Obviously, 1 is not greater than 14.5. And getting 1 usually doesn't mean you got a sample at all. So we just do as is. When we say as is, what we do in normal distribution, wherein we get the z-score of this. So if it's plus or minus 2 hours a week per week of the population mean, then that means plus 2 minus 2. That's when we are asked what would now be the probability that a randomly selected employee would have the average burning time between 35 minus 2, that's 33, and 35 plus 2, 37. Oops, sorry, wrong symbol. That should be not mean but x. Because it's just a randomly selected employee. So we do as is as what we do when we solve normal distribution. So therefore, we find the z-score of 33 and the z-score of 37. That would be 33 minus 35 over 8 and 37 minus 35 over 8. As you can see, we don't apply the correction because, well, it's not applicable because of this. Because here we say that 1 is not greater than or equal to 14.5. So therefore, from here, we can actually see that the z-score of this is negative 0.25. So this one here, oops. So this one here is positive 0.25. Which translates to finding the probability that the z-score is between negative 0.25 and positive 0.25. Solving for this, we actually get the value of 0.1974. Therefore, the probability that a random employee would be working from 33 to 37 hours would be 19.74%. Now, if we apply letter B, if a sample size of 19 is taken, what is the probability that the sample mean lies between the plus minus 2 hours? So now that we have a sample size of 19 that is taken, will we apply our population corrector? Because it asks what's the probability the sample means lie between 35 and 37. So in symbols, that will be probability that the sample mean is between 33 and 37. Now we can see that 19 is greater than or equal to 14.5, which is your 5% of n. Therefore, we apply our population correction. So to do so, for here, we compute first our standard error. And since it's mean, we'll compute the standard error of the mean. So that will be the standard deviation divided by the square root of 19 times our population correction, our correction formula. Oops, sorry. Let's fix that. Correction formula would be the square root of n population size minus sample size all over population size minus 1. In this case, that would be times 290 minus 19 over 290 minus 1. Solving this in our calculator, we get a value rounded off to 4 decimal places of 1.7773. Therefore, this is what we use to find the z-scores for 33 and 37. The z-score of 33 would then be equal to 33 minus 35 over 1.7773, and this actually gives us negative 1.12. Well, the z-score of 37 would be 37 minus 35 over 1.7773, and that gives us positive 1.12. Which now tells us we need to find the probability that the z-score is in between negative 1.12 and positive 1.12. And solving for this, we actually get 0.7372. If you're going to look at above, yes, it has a bigger chance because now the sample size is higher. So therefore, the probability that the sample means of the sample size 19 is between 33 to 37 hours per week would be 73.72%. Now let's move to number 2. Of the 692 passenger vehicles imported by a South American country in a recent year, 117 were Volvos. A simple random sample of 300 passenger vehicles imported during that year is taken. What is the probability that at least 15% of the vehicles in this sample would be Volvos? We are given a population of 692 vehicles. And we are told that out of those, 117 were Volvos. That means the population size would be 117 over 629. And that would be around 0.1860 rounded off to 4 decimal places. Now we get a sample of 300. With a sample of 300, what is now the probability? We are now asked what is the probability that at least 15 of those vehicles, so it can be equal to at least 15% of those vehicles would be Volvos. So first, we see that this if the sample size in 3 is 300, let's check whether that is greater than or equal to 5% of the population, and that would be 5% times 629, which is equal to, computing for that, we get 31.45, which is obviously, 300 is obviously bigger than 31.45. Hence, we apply our population correction. And since we're talking about proportion, the standard error for the proportion would then be equal to the square root of our population proportion, which is 0.1860 times 1 minus 0.1860 all over our sample size of 300. Rounded up to 4 decimal places, we're sorry. Before we do that, we also have to multiply to our population correction of, again, the formula is sample size, population size minus sample size over population size minus 1. So we're going to get 629 minus 300 all over 629 minus 1. Now, we compute that, and we get 4 decimal places, 0.0163. Hence, if we're now going to find the z-score for 15%, that would be 15% minus, since this is percent and this is in decimal, let's convert the 15% to decimal. That would be 0.15 minus 0.1806 over 0.0163. This gives us a z-score of negative 2.22. Hence, we're asked for the probability that z is actually greater than or equal to negative 2.23, which is the same as 1 minus the probability to the left of negative 2.23. And this actually, once you compute it, we actually get we actually get 0.9871, which tells us that the probability that the proportion would be at least 15%, that this is actually the better symbol, not x. The proportion would be 98.71%. So those are the concepts of the sampling distribution of the proportion and the finite population correction.